Hi everyone, welcome to CS168, discussion 8 on TCP. For this discussion, we're going to be talking through reliability and thinking about L4 in our network stack. So you can find all the materials for this discussion at cs168.io. We scroll down here to discussion 8 on reliable delivery in TCP. We can open up the slides in the worksheet that we're going to take a look at today. So let's get started. I'm going to first talk about a scheme for reliability that's a bit simpler than what TCP actually does. And we'll talk about what TCP actually does and what the header looks like for TCP and its behavior. And then we'll go over some problems on the worksheet. So we've been talking about reliability. Up until now, we have learned about how routing works on the internet. And we've been thinking about implementing L3, the IP layer. And the IP layer is providing best effort global delivery, whereas L2 is providing best effort local delivery, and then L1 is the actual bits on the wire. So with a scheme that gives us some sort of best effort global delivery, that works pretty well. As a client, I can send some data and hope that it makes it, and the network will try to deliver it, but won't make any promises. And so instead, we're going to need some sort of scheme on top of this best effort global delivery to make the fact that we're sending over a network that could lose packets transparent. So we don't want the application to have to think about the fact that in the network, there are these packets. Some of them might get lost. If they get lost, they need to be resent. If they get reordered, they might need to do something special. And there are all these things that can go wrong in actually sending our packets. And some of them are listed here. You could lose a packet, and that's a more obvious one. But a packet could also get corrupted. A bit get flipped. Packets could get reordered. Now, think about this for a second. Why is this a problem? If you receive packet 2 and then packet 1, why is that an issue? So it kind of depends on what your data is. If you have a web page and there are 2 images on this page and you receive, there's a single image in a packet and there are these 2 packets, one for each image, then fine. When you receive the second packet, maybe you could display the second image, and then when you get the first packet, you display the first image, or vice versa. But usually, files don't fit neatly inside of a single packet, and so they need to be broken down into smaller pieces. And the problem there is the application is expecting to be given a complete file. It doesn't know what to do with part of a file. And so L4 isn't able to take part of your file, some subset of the packets, and just pass them up to the higher level. The interface that the higher level is expecting is a stream of bytes. And so you can only continue streaming sequentially. You can't jump ahead in the stream and then jump backwards. And so we're going to have to handle this case of packets getting reordered in the network as part of reliability. Packets get delayed, packets get duplicated. All of this stuff should be abstracted away from the application. And so our building blocks to deal with this are as follows. If we're going to want to deal with corruption, we need some way to check that our packet is okay. And for this, we use a checksum. And you might ask me, well, Alex, in IPv4, we did also have a checksum. But remember, in IPv4, the checksum was just over the header. It was just to ensure that the IP header doesn't get corrupted. And in fact, in IPv6, we removed this. So here instead, the TCP header, the checksum that we have is over the header and the entire body. And this is useful because it lets us detect corruption in the content of our packet. So feedback. We do need some way to get feedback. because without hearing back from whoever we're sending to, we have no way to know whether our packet made it. And so using this feedback, we decide whether or not to resend the packet. And usually it's, if we don't hear back from the person receiving, confirming that they've received the packet that we've sent, we're going to send again. Now, the next tricky question you get into is, how do you know when to send again? And we talk through in lecture how you come up with a timeout for that. And finally, you have to know what to resend and what to be sending next. And for that, we have this notion of sequence numbers. So with these building blocks, we're going to construct some sort of reliability scheme. And within this scheme, we're going to have these different parameters that we're going to be tuning. One of them is the window size, saying how many packets am I going to send at a given point in time. The other is, what is this feedback going to look like? What kind of feedback do we get? We've talked about just regular single packet acts. We've talked about cumulative acts. We've talked about full information acts. These are all different kinds of feedback. Of course, we also have to think about how are we going to detect the loss that happens, and then how do we respond to it. So I'm going to start off talking about a simple, though not advisable, and I'll talk about why not advisable in a second, a simple scheme that would provide reliability. It's not what TCP does, but it's a useful starting point for us to build from. So let's describe this hypothetical kind of algorithm called GoBackN. It's a sliding window protocol. And the sender is going to have a window of size W of transmitted but unacked packets. And so here we see this view of some sequence of packets. This green set of packets on the left is already sent and acked. This yellow set of packets is inside of the window. And notice the window starts from the first packet that hasn't been acked yet. And this is the set of packets that have been sent but not yet acked. These blue packets haven't been sent yet, but they are eligible to be sent. And packets past the window are not usable yet. We can't send them yet. And we're going to keep track of a timer for the oldest in-flight packet. So if we don't get an ACK for that in-flight packet before we time out, so before a certain amount of time passes, we will time out and resend all W of these packets, starting with the one that lost and everything else in the window that was already sent. And this way, the receiver doesn't ever need to deal with packets that are out of order. This is something that's interesting. Because if any packets are dropped, or if any packets are not acked, which could happen if they're dropped, or if the receiver decides to just throw away packets which are out of order, the sender is going to resend the full window. So let's take a look at what this looks like without errors. So go back in without errors. We have this nice animation that Sarah, one of our other TAs, spent a lot of time making. We have a window of size 4 here, and a sequence of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 packets that are being sent. So here, the very first packet gets sent, then the second packet, third packet. Now, this first packet got sent, and at this point in time, it's received on the other end. And that's great. This packet wasn't dropped. So the receiver is going to generate an ACK. Going to reply back within a second. But here we have all 4 packets have gotten sent. And on the other side, all 4 of these ACKs are being generated. And so we have the ACK for packet 1 arrives back at the sender, and the window is able to slide 1 forward. I'll just point this out again. So as soon as this ACK arrives, well, the first packet is ACKed, and the window slides forward. That reveals a new packet that hasn't been sent yet. And so immediately, our sender is going to send the new packet that's now been enabled to be sent in the window. Then the second packet is ACKed. The same thing happens. The window moves forward. A new packet appears that hasn't been sent yet in the window. And so our sender is going to send that packet. And continuing on, This continues to happen with each ACK. And the window just keeps marching forward, right? So here 5, 6, 7 are sent. On the other side, 5, 6, 7, or 8 are received. And all of these ACKs are sent back. And the window progresses forward. So the scheme seems to work pretty well when there are no dropped packets. But the intent of the scheme was to provide reliability. So let's see how it handles errors. Well, in GoBackN, we're going to start with the same 1, 2, 3, 4 window. And yes, in the previous slides, we had this nice pretty animation. Here you get the idea of how this window moves. So instead, we're just going to write these out here in little brackets, where the brackets are the window. And you can imagine there's 5, 6, 7, 8, 9, going forward onwards beyond these brackets. And you'll see how these brackets are going to change the data that they hold. So first packet 1 is sent, and then 2, then 3, then 4. And on the other side, we get back, generate ACKs 1, 2, 3, and 4, and those are returned. Now, when ACK 1 comes in, what happens? The sliding window is going to move 1 forward, which means 1 will no longer be part of the window, and now 5 is in the window. And ACK 2 is going to arrive, so that means that we can remove 2 from our window, move the window forward, slide it. 6 is revealed, and so we send 6. But here is where we have a problem. We're going to find that in this scenario we've constructed, packet 6 is going to get dropped. So we have 5, 6, 7, and 8 are sent. 6 is dropped. When packet 5 is received on the receiver side, an ACK will be generated and sent back. And that's encouraging because the receiver receives that. Everything seems like normal. The window slides 1 more forward, and we have 6, 7, 8, 9. But then 6 does not arrive. And so that means that the next packet that the receiver gets is actually 7. And we discussed at the beginning here of these slides that in this scheme, we're just going to drop packets that are out of order. So if you are waiting for packet 5, in this case, packet 6, and you receive packet 7 for some reason, you're going to ignore packet 7. The only thing that you want right now is packet 6 and nothing else. And so you're going to send back the last thing that you ACKed, which is ACK for packet 5. And at this point in time, there's no other packets really in flight. And so at some amount of kind of timeout here that's configured as part of our protocol, this packet is going to time out, which means that the sender has waited long enough for an ACK for the packet that it sent to assume that that packet must have been lost, otherwise an ACK would have been sent back. And that means on timeout, in our scheme, we resend the entire window. So we send 6, 7, 8, 9, and everything makes it through, and so the other side has ACKs 6, 7, 8, 9, and sends those back. Okay, so that's our simple GoBackN scheme. TCP improves on this, and we'll talk about how in these next slides.